Good morning, good afternoon, or good night, everyone, and thanks for being here and attending this session. My name is Michele Polese, and I'm a research scientist at the Institute for the Wireless Internet of Things at Northeastern University in Boston, Massachusetts. And today I'll present a paper I co-authored with Francesco Restuccia and Tommaso Melodia, whose title is DeepBeam, Deep Waveform Learning for Coordination-Free Beam Management in millimeter wave networks. Something that I'd like to mention at the very beginning of this presentation is that we have a website for the paper, deepbeam.net, where you can find links both to the code that we used and developed for the paper, and most importantly, the datasets that we collected for this paper. It's an experimental data set on which I will give more details later on, but I invite you to visit the website, download the data set, play around with it, and reach out in case you have any questions. So this is the outline for today. First, I will describe the motivations for the paper, the context in which DeepBeam was developed, and the main contributions of this paper. Then I'll spend a few words on the framework and on a use case in which DeepBeam can be relevant and provide a performance gain. I'll go through the experimental evaluation that we did for DeepBeam, and I'll draw my conclusions. So the context in which we operate and in which we develop DeepBeam is that of millimeter wave mobile networks. 3GPP-NR, which is the 3GPP standard for the 5th generation of mobile networks, will support frequencies that go as high as 52.6 GHz with extensions to 71 already planned. This allows to increase the data rate from the 1 gigabit per second peak data rate of LTE to 20 gigabit per second of peak data rate in 5G. And this is due to the fact that at millimeter waves, there is a very high availability of bandwidth. So consider this figure, which is taken from one of the early papers that proposed the usage of millimeter wave for mobile broadband systems. So all cellular mobile communications nowadays are confined into this very small area, roughly below 3 gigahertz, or you can even say below 6 gigahertz. But above this, there's and up to 300 gigahertz of bandwidth, there's a potential 252 gigahertz of bandwidth according to PNCAN. And like other millimeter technologies even exploit these 7 gigahertz that you have here. So there is really a ton of bandwidth at millimeter waves that can be exploited to create ultra-high data rate links. However, with the potential, you also have a lot of challenges. So as you may know, the higher the frequency of the wave that is propagating, the higher the path loss the signal incurs, considering the same antenna size. So there's a limited coverage. This is the first main issue that can be partially compensated with directional transmissions. But as we'll discuss later on, directional transmission themselves introduce challenges throughout the whole protocol stack. And then the other challenge that you have is blockage. So millimeter wave signals are easily blocked by the human body or by obstacles, buildings, cars, and so on. So directionality, as I was mentioning, is one of the main challenges in terms of system design for millimeter wave mobile networks. So with directional transmission, the transmitter and the receiver focus their energy in very narrow beams. And this allows eventually to increase the link budget thanks to a higher beamforming gain. However, the transmitter and the receiver need to point the beam toward each other. Otherwise, as I show here in the bottom left of this slide, if the transmitter and the receiver are misaligned, so if they do not point their main lobe toward each other, the beamforming gain could disappear. And this would basically remove the benefit that the directionality introduces in the whole equation. So there is a need for procedures to manage the directionality in two different steps of the whole connectivity of the user. So the first one is the initial access. So there is a mismatch in the discovery range between, for example, sub-6 omnidirectional signals, but even between 28 gigahertz directional signals or 28 gigahertz omnidirectional signals. So you cannot use omnidirectional signals for your control plane, because otherwise, if you then use directional signals for the data plane, you would have a mismatch between the range that you can achieve with omnidirectional transmissions and the range that you can achieve with directional transmissions. So you need directionality even during cell search. Second is you need tracking. So as the user moves in the scenario, the optimal direction, the optimal beam with which the base station is served may change. And this means that the base station and the user need to keep track of the optimal direction with which each other can be served. So traditional bit management, as done in millimeter wave networks, involves the transmission of pilots and oftentimes an exhaustive scan. So it's represented here. The base station has multiple pilots that are transmitted periodically, interleaved with other data transmission to avoid increasing the overhead too much. And the receiver, the mobile device, also can have some direction to scan. Okay, and eventually, to allow a complete scan of the combinations that are available, which is eventually what results in the possibility to identify the best beam pair to be used, you're going to end up with a very high latency and overhead. So this is where we think that deep learning can help. So you have a few blocks, a few challenges on millimeter waves: the directionality, the blockage, and the need to support high data rates. But coupled with complex control procedure and the need to coordinate different network nodes and do that quickly to avoid losing a lot of data, means that you need very tight control loops. You need very efficient control procedure. And the initial access, as it is designed right now, for example, in PNR, assuming an exhaustive scan, is very inefficient. And in this, we see AI play a crucial role to optimize 5G and millimeter waves with some predictive or autonomous control policies. And this is why we introduce DeepBeam, which is a framework that allows to perform AI-enabled beam management. So recall, this is the traditional beam scan procedure that we've just seen, and only these signals, the pilots, can be used to basically identify the best beam combination to be used. With DeepBeam, we use deep learning at the waveform level. So we learn on the IQ samples of the received signal to identify a couple of elements: the angle of arrival, and which is the beam that the user is transmitting. And we do this most especially by eavesdropping any kind of transmission, not only pilot transmission, but also data transmission. So this eventually, as I'll show you in a bit, allows to reduce both the latency and the overhead. So in terms of main contribution, DeepBeam is the first waveform learning framework for millimeter waves. And thanks to the combination of deep learning and the DeepBeam scanning procedure, we can speed up the initial access and the tracking procedures. And most importantly, we do this without the need for any explicit coordination between the transmitter and the receiver, and without the need for pilots. The second main contribution is that we validate DeepBeam with real experiments, which I think are really important when it comes to learning at millimeter wave frequencies, because of the channel characteristics at millimeter waves, and because of how the devices are designed. And besides this, given that you need to complete the procedure in a matter of milliseconds, if not microseconds, the design of experimental pipelines for millimeter waves is particularly challenged. So I think that for the application of machine learning into millimeter wave, into the millimeter wave domain, experiments and experimental datasets are really important. So we have a dataset of 4 terabytes of raw waveform that we released on this website, deepbeam.net. So feel free to download it and play around with it. And it contains a combination of multiple transmit and receive configurations placed in different locations and with multiple radios from NI with the side beam front end and per radio. And I'll tell you more about the dataset in a bit. So DeepBeam achieves an accuracy in classifying the transmit beam that goes as high as 96% for a 5-beam codebook, 84 for a 12-beam codebook, and 77 for a 24-beam codebook. And the usage of DeepBeam allows to reduce the latency as high as 7 times with respect to the 5G NR initial beam sweep with a typical configuration, for example, with 12 beams. And we performed this analysis considering an FPGA implementation of the DeepBeam neural networks to have a fair comparison between the different systems. So let's take a look at what DeepBeam is in a nutshell. So what does DeepBeam learn? DeepBeam exploits basically over years ongoing transmission. So in this example, you see the transmitted waveform that is received here, goes through the receiver chain, and basically DeepBeam taps into the IQ samples that are processed by the receiver chain. So you have complex IQ samples on the IQ plane, which are fed into a couple of convolutional neural networks. And the first thing that DeepBeam learns is which beam is being used by the transmitter. At the same time, in parallel, another convolutional neural network identifies what is the angle of arrival of the signal on the phased array of DeepBeam. And it does this without relying on multiple RF chain, which are necessary, for example, for many other AOA tracking algorithms. It does this with a single RX chain. And finally, once DeepBeam has collected these 2 pieces of information, it performs its adaptation step by basically selecting the received beam, which corresponds to the optimal angle of arrival, and informing the base station of what is the transmit beam that the base station should use to communicate with the user. So the inference engine of DeepBeam is based on a convolutional neural network. And let's take a look here at the different steps that are involved. So on the top left, you see 3 different beam patterns for 3 different beams. 2 of them actually are very similar, especially in the main lobe. So beam 11 and 12, the yellow and blue, are very similar. And we have a beam 0, which has a main lobe, which is very different, in a very different direction with respect to the average. So these beams translate into some imperfections in the IQ plane that can be captured by a convolutional neural network. So the convolutional neural network is particularly effective in this because it can identify this imperfection independently on where we are located in the received waveform. And effectively, it manages to correctly identify and classify the beams. So just to show you an example, here we show the average activation value of the first layer, the first convolutional layer, for different beams, for the 3 beams that are shown here. And as you can see, the positive activation values are different for beam 0 and the 2 other beams. And instead, for beam 11 and beam 12, which have a similar beam pattern, the activation values are still different, but they are, let's say, more similar with respect to beam 0. So this shows that effectively a convolutional neural network can be used to distinguish the transmit beam as part of the DeepBeam framework. So the one use case that we identified is the initial access in 3GPP-NR. So during the initial access phase, a cell search is performed with the base station transmitting periodic signals called SS blocks grouped into bursts. And bursts are repeated with different periodicities. So, for example, the smallest periodicity is 5 milliseconds, and in this 5 milliseconds, you have 64 of these directional signals transmitted by the base station. A typical periodicity is, for example, 20 milliseconds. So, in the paper, we have a complete analysis that calculates how long it takes for a 3GPP-NR networks to perform an exhaustive search given a certain codebook using the actual parameters from the standard. And we compare this analysis with an analysis for the time it takes to DeepBeam to collect the data it needs, process this data inside an implementation, an FPGA-based implementation of the neural network, and basically return the results that are needed. So this is a fair comparison that assumes for both the baseline and the DeepBeam framework the overhead given by the need to collect data and collect enough information. So just to show the analysis, you can find it in the paper. I'll skip it now for the sake of time. But I want to show you the final results of the analysis. So as I mentioned, we use for DeepBeam an FPGA implementation of the CNN, which has basically almost half a millisecond for the end-to-end delay and for 0.44 milliseconds for the slowest layer, which is key if you want to pipeline. This is a baseline implementation, let's say, that can be improved. But even with this basic implementation, basic FPGA implementation, if we compare the time it takes to perform a beam sweep with DeepBeam with respect to 3GPP-NR, you can see that we have at least a 2x gain here with the highest with the smallest periodicity for NR, so with the highest overhead for NR. And in a typical configuration with the SS burst repeated every 20 milliseconds, we have a 7x gain. So to evaluate the ability of DeepBeam to distinguish different angle of arrivals and different transmit beam, we performed a multi-radio data collection at 60 GHz using 4 different side-beam analog phased arrays connected to the NI mmWave transceiver system. and two PyRadios software-defined radios that are based on digital beamforming, but that we used as analog radios. So the dataset has been collected with multiple spatial configurations, multiple combination of the transmitter and the receiver device, and different codebooks. So the dataset has been, as I previously mentioned, is publicly available and has been published at deepbeam.net. So we hope it can become the basis for more and more benchmarks from the research community. So just to show you some results, this is the classification, the average classification accuracy for different codebooks, the 12 beams and the 24 beams codebook. And the accuracy is rather high, with errors that often happen among neighboring beams. So beams that, as we've seen earlier, have a very similar profile, especially in the main lobe. We also evaluated the impact of the input size. This is, for example, what we can achieve on the PyRadio, the 5-beam dataset, which achieves an accuracy of as high as 91.56%. We evaluated the impact of the SNR. So with the previous results, the mixed SNR, low, medium, and high. Of course, as expected, with low SNR, the accuracy decreases, but this can be compensated, for example, by doing first the angle of arrival adaptation step and then doing the transmit beam classification, which will lead to a high SNR situation in which the accuracy is very high. We evaluated different spatial locations, as you can see here on the top left, top right of the slides, and the results are similar and consistent, showing that DeepBeam can learn and adapt also when deployed in different configurations. So the not only with a different spatial configuration, but also with an obstacle in between the transmitter and the receiver. Then we tried to perform training and testing on different devices. So training on with the dataset collected on one device and testing on another. So you can see that the features learned by the CNN are a mixture of antenna-based and independent, and antenna-independent feature, because the accuracy decreases, but it does not drop to random classification. And even more, if you train and test with a mixed dataset, you can achieve even better results, showing that DeepBeam has a promising potential for generalization. So going to the conclusions, so we showed for the first time that deep waveform learning is effective at millimeter waves, and that it enables pilotless approaches that can improve the overall performance. So you can do beam management even without pilot or explicit coordination. This is the first paper on this topic, and there is a lot of future work that can be done starting from this. So for example, something we're looking into is how we can improve the generalization capabilities of DeepBeam to improve even better the results on what you achieve when you train on one device and you test on another, or when you train on a mixed dataset. In addition, we plan to test different scenarios, more radios, more heterogeneous radios, and increase the number of parameters that we investigate. So, as I mentioned, the dataset has been published, is available, and is available at this website, deepbeam.net. So I thank you all for attending this session. And if you have any question, I'm available now, or feel free to email me at this address. Thank you very much.